we will see some general details about neural networks. That's what is the objective of this class, which could potentially help you while you are building your own neural network. So let me, even before that, let me start discussing about these integration functions. What was our integration function earlier? Let's say g of x bar is equal to, assume that I have k neurons in the previous layer, right? And w, well, this could be for a ith neuron in the next layer. It could be wij into, assuming that xj is the previous neuron, plus something like, if you want, I can write wi0, some biased value. Hope you all remember this, right? This is how we have done an integrated function earlier, but this need not be the only way. That's what I want you to realize. This is one possible way of having an integrated function. Okay, of course, this has come for us from the knowledge of W transpose x bar plus W naught, which we got as a discriminatory function for a linear separable case. That's where we started with. But there is no reason why we should stick to just this type of integrated function. Okay, say this is, by the way, doesn't even know the name of this integrating function. You should have, those who are taking deep learning might have come across. This neuron model has a specific name, which we haven't as such discussed in our class. Anybody has any idea? Yeah, it's a modeling of a perceptron, is a mathematical model for a neuron. This is called as a McCulloch-Pitts neuron model. This is referred to as, just to ensure that I don't write the spelling wrongly, MUCULLOCH, McCulloch-Pitts neuron model. And of course, in this neuron model, what you have is the activation function is a step function, and your integrator, okay, we are now, instead of calling it as a summation of just linear terms, we are calling it with a generic name, integrator. Your integrator is a linear combination of your feature vectors. So this is referred to, this is a, you could think of the simplest model that you could come across, and this is referred to as McCulloch-Pitts neuron model. Perhaps, I guess these are the two others who had proposed it and might have come on their name, or quite possible that the neuron model would have been proposed by them. So refer that, I am not aware of that. This is one integrating function. Other possibilities are also there. For example, I could have a quadratic model for an integrator instead of having such a linear model. So how it could be, for example, in similar lines, I could write gi of x bar is equal to j equal to 1 to k. Can you tell me perhaps how the quadratic model could be like? Any guess? Wij into j square plus w naught. That is all. Wij xj square. You have a quadratic term here in the integrated function. This is also possible. This is referred to as a quadratic model for your integrated function. Now, for some strange reasons or some unknown reasons, assume that I have some points like this, and maybe another class points are like this. I have the another class points. What kind of discriminate the function would you expect there? A circular discriminant function will do the job for you. You could have something like this, right? Even with a single neuron should be able to solve that. Any idea that is referred to? Of course, what would be that? If I move on from this x1, x2 to higher dimensional, let's say 3-dimensional space, what would be that? Sphere, right? So instead of quadratic model, the other one you could call it as spherical model. You could have there. How does that look like? Gi of x bar is equal to j equal to 1 to k. Hope that makes some sense, right? Plus, of course, you could have w naught or wi naught, whichever you call there. So wij times xj, quadratic model xj square, the spherical model xj minus wij whole square. Of course, in every place, these are the feature vectors. These are the weights that you are going to figure out. Square or cube? Huh? Why is it so? See, it is like x minus a whole square plus y minus b whole square equal to r square. So something like this will be the equation of my circle. Let us see it in terms of circle. So it is close to that. xy you replace with x1 and x2. Okay. And this could be w1 and w2 or wij, you have it. Okay. And this could be plus w naught. Okay. Square, you could consider that. That is equal to 0 would give you the equation of a circle, isn't it? So this is you go to one more level, that would be a sphere. Hope you see why this equation is referred to as a spherical model of an integrator. Okay, and you can, this list can go on and on. You could come up with, once you see the way your feature vectors got distributed, if you have the fortune of knowing how they are distributed, which we might not be having that luxury most of the times, but if you have some idea, this is something that could help you with. Maybe one more thing that people were commonly mentioning, I'll write that, and with that we'll move on to the next thing. So this is called as polynomial function also you could have here. Nothing stops you doing a polynomial model for your integrator. So let's say, let me write that out here. So this is gi of x bar is equal to, let's say m is varying from 1 to k, n is varying from 1 to k. See, my assumption here are there are k neurons in the r minus 1th layer. So those are what I am writing as 1 to k there. So hope you are all clear with that. Okay, n equal to 1 to k, some w I m n into x subscript m, x subscript n plus xm power alpha m, right, plus xn to the power alpha n, this whole thing plus some wi 0. Have a look at this. You are multiplying two neurons here essentially, xm and xn. So that's why you got a, and then depending on the value of m, you could also take a call on to what power you want to rise and whether you want to have it or not. Okay, you make it 0, then it is no more there. And similarly, you can have for the another one also, you can have it. This list can go on and on. The take home message here is, don't be under the impression that linear model, the non-linearity has to come only by increasing your neurons and having a hidden layer followed by output layer. If you have some clear understanding of, in any special case, the type of the spread of your feature vectors, if you have any idea about that, there could be instances where you could figure out a better one. Clear? Good. So that's as far as the integration functions are concerned. Activation functions we have already seen in the earlier classes. Hope you remember that. So activation functions. What was the common activation function we use? Yeah, before that, for all theoretical purposes, we have done with the step function, and that step function is varying from 0 to 1 we have taken, right? Where this being 0 here, any negative values, one class as 0, another as 1 we have taken. Then another way considered is, sorry, this is -1 I have drawn. It could have been 0 and 1 also, right? -1 and 1 people consider that, because all you need to do is sign off g of x bar in your program. If you are writing just sign off g of x bar, either negative or positive, you will get -1 and +1. That is the reason why they consider, as far as I understand, -1 and +1 instead of 0 and 1. Okay. The same logic holds for sigmoid function. That is more practical. Why did we discard it in all our further analysis that we have done? What was the reason? It is not differentiable. We have moved to sigmoid function. What was the sigmoid function? F of, let's say, x is equal to 1 by 1 plus exponential of minus ax. Okay. Make a note here. This is a scalar quantity. What would be if you consider this gi of x bar? Okay. What would be this? Or I could have written this as minus a times w transpose x bar also. I could have written that if you want, right? Because whatever integrator out of that, again, this is w bar is varying 0, L dimensional, L plus 1 dimensional, you scale it up so that the bias is also absorbed into it. If you consider it minus a times w transpose into x bar. And yeah, in practice, unless you have a reason to do so, you might just simply make this as 1 also. That is quite common. You just simply consider 1 by 1 plus exponential of minus x. Okay. So this, if I have written w transpose x bar, I should be writing here also w bar transpose times x bar. I should be writing here. That's the input coming from the integrator. Okay. So this is one thing. And then we have also discussed there are family of curves there. Tan H function. Okay, you could look at the definition, and this could be, then again, we also did something. This, how does it look like? This is a kind of, if you have a step function from 0 to 1, what, or 0 to 1 also you could consider. This is my, okay, my drawings are too good today. Okay, so this is like, is giving you this, correct? And if you want it from -1 to +1, that also we hope you all remember. I made it as 2 times. So that's varying from 0 to 2. I want it to -1. That's all you have to do that. And that is as far as, this is the second one I wanted to, first I wanted to mention you about integrator functions and activation functions. So another thing I wanted to bring to your attention is all the back propagations and everything we have worked out are one particular type of neural networks. What is the type of neural networks? Feed forward neural networks. The connections and the transmission of information goes in forward direction only there. There is an input layer. There could be multiple hidden layers. Finally, output layer, of course. The gradient propagation, gradients are weights are adjusted in the back propagation. That is only as far as the adjustment of the weights are concerned. But if you look at the way you have written your integrating function and everything goes on, it is only in one direction. That is, so I would call this, for example, types of neural networks. So that is feed forward neural network. What could be else? What else could be the possibility? Any idea on what it is referred to as? Feed backward neural networks also could be there. How do they look like? For example, these are your inputs here coming. You have one hidden layer here. Assume that I have two neurons in the output layer. Now, what could happen here is it's not just this way. You could have another connection going on here also. Similarly, within the neurons also, between the neurons also, there could be a connection going on in either ways. It could go on. Okay. This again, you have to be careful. The way you compute then the gradients and adjust the weights will be different. You have to slightly do it in a different way. But of course, the basics would remain intact and same. But you have, this is something we have not discussed much. Again, when you have too many layers and too many neurons, then the gradients vanishes. There is a problem of vanishing gradients would arise. So these are all, these connections have a purpose here, particularly when you have too many layers. You want to give this information right away as a feed to something else which is there after many layers after this, not just the immediate layer, but maybe 3-4 layers after that also. This information you want to pass, of course, with some weightage there. That is where you would get feed backward neural networks also. There is another one also here you could keep. Any idea? Right, recurrent neural networks. This also, these two will not get an time to discuss, but at least it is good to know here. This is something which carries a memory of the temporal information. If you are talking about, let's say, a signal which is varying over time, you are doing, let's say, a natural language processing. You are going to tell, if you would have seen when you are typing something in your Google search, it tells you the possible options that are there. That's a machine learning algorithm which looks at the previous words that you have typed, and based on that it will be able to tell you what could be the next word that you would be potentially typing. So there is something inherently, there is a memory in that, and these kinds of models you would see, and again I think LSTMs comes under this, correct? LSTMs falls under the recurrent neural networks, okay, and gated recurrent units. There are quite a lot of networks are there. These are all recurrent networks which have inherently a memory. So if you are talking about speech, you will call it as temporal memory, because over time it keeps track of that. If you are talking about images, it could be the image before that. If you have a 3D image, you might be running your neural network for one image, but previous image and classification that happens in an image above it, a slice above it and slice below it. If you're talking about 3D image and processing it slice wise, 2D wise, that carries some information. So these are the more, you can expect more efficiencies with networks that keep track of or keeps in memory what's going on in subsequent layers. So these are referred to as recurrent neural networks. Okay, we will not have time to go through any of these things, but for now it is good enough for you. You can explore it as and when you require, but hope this is clear. These are the common. Again, you could go on and on here, single neuron model, multiple neuron model, and all you could add and go on. Okay, so the next fourth point, clear? This third point is clear, right? Okay, the fourth point I want to make it clear is regarding the choice of the hidden layers, choice of number of hidden layers. How many hidden layers should we have? Suppose I have a nonlinear classification problem. What do you think? How many hidden layers should you have? Suppose I give you the license. You can have any number of neurons in a given hidden layer. Then what do you think are the number of hidden layers required? In principle, one hidden layer should be good enough for you to arrive at any nonlinear classification. If you remember, the hidden layer, what it does, just even if you think of the integrator, McCulloch's-Pitts integrator summation thing, each one will give you a line there, correct? So that will, for example, these number of layers should be such a way that each one should somehow, from each class in your training data set, you should be able to separate them and bring them into one of these regions. As long as you are able to separate them, the next layer will do and/or operations with all these things. Essentially, your output layer, you could do it such a way that it is there in this, or it is there in this and operation. That is essentially what we were doing. With that, in principle, you should be able to achieve any nonlinear classification, or you could call, if not classification is very specific, you can call it as nonlinear mapping. Okay, the next question would be how many however, there are good reasons where you would consider more than one hidden layer. What the way you could interpret is, suppose in your classification problem, if you're after applying a transformation on your data, if your classification problem gets simplified, okay, then it is worth having more hidden layers than keep on increasing the number of neurons in a given hidden layer. It is not very difficult to, we are not going to formally deal with it, but you could think of it this way. You all know the matrix operations. Suppose I have a vector X. I multiply with A. What does this do? It is equivalent to applying a transformation on this vector X. So, see, what is all you are doing here? W bar transpose times X bar. That's all you are doing for each one. So, you could think of the first hidden layer as if it is transforming the data. Okay, so the next hidden layer, it will convert it into regions. Otherwise, number of neurons, although in principle you could achieve that by increasing the number of neurons, you could do it this way. Just consider this problem. Okay, so suppose if I have to solve, well, with more increasing number of neurons, you may get this line, this line, this line, this line, and it is possible. But assume it could be even more complicated. If I have this, maybe one more line, it can go on and on. In principle, you can achieve this, but assume that there is a transformation you apply on it, which makes your job easier, right? Then that is the reason why, although in principle, one hidden layer is sufficient to perform any nonlinear classification, in principle, you will go with more number of hidden layers. You could think now, when you have more number of hidden layers, you could think of it or interpret one way of interpreting, if not the only way of interpretation, is that you are doing some transformations on the data using each of these hidden layers. These transformations, you could think of it as translation, rotation, scaling, okay, any of these linear transformations. Of course, then there is a non-linearity also, perhaps, because you have multiple neurons there coming in the each hidden layer. And of course, you could also see now, this is a very generic one. If you look at all your DFTs, you could write it as AX, right? Transformations. If you have looked at it, you could write them as some matrix operations. If you have done it, it's nothing but projecting your data onto a different dimensionality there, right? So that way also you could see, in principle, again with hidden layers, again, the very assumption here is that it somehow figures out what is the transformation to be applied there. Your network should converge essentially because you are randomly initializing your weights. Now each hidden layer is in such a way that we again come back to square one and assume as a black box that it can somehow manage with it. Under this assumption, you can say that okay, it will do or iteratively, it somehow figures it out. But the important point to convey here is you could there are quite a few practical instances where you just will not restrict yourself to going on and on, increasing your number of neurons in one hidden layer, rather have multiple hidden layers. You could think of each hidden layer as applying some transformation on a data, on your training features. Okay, is that clear? Now, that is as far as number of hidden layers are concerned. So depending on how many kinds of transformations you want to apply, there is no way that had it been 1, 2, 3, somehow you could manage to see the feature vectors. Suppose if you are feeding your network, your features, you have 100 by 100 image. Okay, assume that you are giving all of them. How many are there? 10,000 as your features. You are in 10,000 dimensional space. Correct. So you can't really see which transform got applied. That is kind of, you could think of it as a limitation if you are blindly feeding everything, or if you have a powerful machine and you don't care about the time and computational complexity. And if it is converging, that's the best thing that's happening. So you could think of it as even when you don't see any specific parameterized pattern there, still it can work. So you could interpret it in either ways. Is that clear? Okay, good. So the next question is, how many neurons do we need? Okay, that's we from there we are wrapping up about hidden layers. How many hidden layers should be there? But then another question is, how many neurons should we have in each layer? How do we know? How should we go about it? And how should we take a call about that? Any ideas about that? So choice of, so fifth one I'm saying that is number of hidden layers. So now the next one I'm talking about is your choice of number of neurons in a given layer. Let's restrict ourselves to one hidden layer. How do you think we should approach this problem? Any thoughts about that? How should we know how many should be there? You would have 100, 1,000, 10,000. So how many? How should we go about that? Not really. Is it dependent on the number of outputs, or is it dependent on the complexity of your separation in the feature space? See, number of outputs may be just a single class, but if my data is very jumbled, so if they are very separate, one neuron is enough. So it is not about the number of outputs. It is more about how separable the data is. There are lots of theorems and lots of papers you would see. For example, just to name one, suppose if you have k neurons and assume that the number of inputs coming there are m. So k in your current layer, m inputs are coming to that, assume a single hidden layer. Okay, m feature vector dimension is m. That tells you that kc0 plus kc1 and so on plus kcm. This would be the number of regions that it would generate. So depending on how many regions you would expect in that, you choose the value of k. Again, here the assumption is k is less than, if you call this varying one up to m as high, k less than I, this is what it gives you. There are lots of papers. There is a lot of literature on it. But again, if you consider images, this shoots up like anything. As I was mentioning, consider a simple 100 by 100 image. How many feet, if you are not doing any histogram and then feeding it, you are simply feeding the whole image as your feature. Each pixel is a feature for you, assume that. If you are doing digit classification, perhaps that's the assignment that you will be doing in your deep learning thing. If you are simply giving your entire image, each pixel as one feature vector, and if your image size is 100 by 100, 10,000. So consider this 10,000. See, that's too big, in fact. So not very practical thing. Okay, or maybe that is one, because this k comes from number of neurons, still okay, but number of regions that you would expect could explode with this. So this only gives you kind of an upper limit for number of neurons, not very helpful. So any idea on how people address this problem? Or imagine yourself the first person to think about this problem. So what would you suggest now? How would you go about it? Consider a very simple case. I have some feature vector is fixed now. I have just one hidden layer. Assume that one output is there in my output layer. How do you solve this problem? What would you do? Right. Here also consider that there could be, that's a very good answer. That is perfectly fine. Your answer is that you keep on increasing until and unless there is no more misclassification. Correct? That's a very good approach. It works perfectly fine, provided you have a very clean separable data. There could be noise introduced into your data, or the feature vectors that you are considering might not give you such a nice classification. There could be always some spillovers from one class to the other. Now you tell me how you do that. Still your approach is your approach is applicable. Let us see with some illustrative picture here. Suppose I have one class here. Okay, maybe better I will draw some boundary and then I will okay. So what could happen here that makes me to keep the dots easier? Assume that I have one class here, okay, and another class here. So one class with this cross marks and another zeros. If the approach you mentioned, what it will do, it will increase its neurons to such an extent that it will cover every guy here. This is as far as your training data is concerned. Then what could be the this is perfectly fine if there is no noise, or you have chosen the right feature vectors such that they get separated. But the moment you are done with your training and you go to testing, then you might realize that there could be now some points here, but this has given you say this is, it is not line 1, but let me just still call it as L1 and L2. These are two discriminant hyperplanes I should call. So maybe you don't want to see line there. Okay, hyperplane HPL1 and HPL2. If you keep on increasing it, it will go something like this. But when it comes to testing, yeah, it doesn't have really a very separable stuff. This might happen. Any solution for this? How do you address this problem? Which Euclidean distance? Because you don't have a testing with you. How do you address this problem? So with this, what would be the consequence of it? I'll tell you. If you take the epochs here and j of w bar or whichever the function you are computing, the last function you are computing, as you are fine tuning, assume that the second, I have told you 3 methods, stochastic method, you are taking each one and doing that. This might somewhere start and nicely go like this for a training data. But when it comes to testing, it may shoot up after some point. So this is where typically in all your machine learning algorithms. First thing you do is you separate the data also into training, validation, and testing. Your validation in a way ensures that you are not overfitting things. If you have, let's say you have a data of 100 feature vectors are there, training data set of 100 feature vectors are there. What you would do, let's say you would use 60% of your data, that means 60 feature vectors for doing the training. With that, you do a validation also. Whether you are overfitting or not, you will see with the validation data. The moment it is overfitting and let's say it is shooting up, you will not any further increase your neurons there that you are using. And then of course, finally, in a way, it's a kind of a mock test. Okay, you have taken 20% here. The rest you are doing, this is again provided you should have enough data also. Otherwise, you look at for some data augmentation approaches. So there is a training, validation, and testing. This is an important thing. Let's say you might use 60% of your samples here, 20% here, and 20% here. But then you started with some network and you realize that this is shooting up. What should you do then? You have to somewhere start. One thing I told you is some analytical expressions which might not be very helpful. Then there are two approaches to build your network. One is, as you said, you start with a very big network. Then you keep shrinking your network such that you get reasonably good results. Another approach is you start with a small network. I think the third approach is what you are mentioning. Then you keep on increasing until this phenomena doesn't happen. Even here also the loss function is coming down over time. You do that. The moment you see that it is increasing, then that means you are doing this too much of a overfitting for separation of this. That's where you should stop. And there is something referred to as pruning, where you would look at the weights that are there at each neuron and see how much it is contributing. If it is shooting up too much, that is the time that's why you will see it's W bar is equal to alpha times W bar. Okay, this is at each neuron you will look at, and let's say this could vary from 0 to 1. That means something whose weights are become small, you will make it much smaller. And the moment they are below a threshold, you will drop that neuron. Okay, this is where you go for the war with a big army. That is a over segmentation you have done. Feeding your army itself is and managing that itself is becoming a problem. You drop those guys in between. Another is you gradually increase it until and unless you feel that this army is good enough to solve your problem or create a problem. I don't know. Okay, so this is referred to as pruning, where you will even if you are doing later using any PyTorch and other things, there will be functions like a dropout. At what value of that you should drop out, what should be the alpha you should pick up, and all those things will be there. Okay, so that is as far as this is called as heuristic weight update. Okay, this the sixth one. This point is referred to as heuristic weight updates. And one more important point, look at this W bar transpose into X. This is what you are computing, and then try your whole J is dependent on that. Suppose your feature vectors have X bar is nothing but your feature vectors. This could spread different ranges. For example, one of them is angle, assume that 0 to 2 pi only it can vary. Okay, something else could be a translation, it can have a larger value. So then what would happen for those of things for which X is very high, that kind of hijacks the rest of the features. So another very important thing that you should keep in mind while you work on all these problems is that your normalization of your feature vectors is a very, very important thing that you will be doing. Okay, so this I would say as normalizing the input features. That's another important thing, normalizing your input features. Then the last point with which I would leave you is, how do you initialize these weights? You need to, hope you all remember the backpropagation algorithm. You need to somewhere initialize, then only dou z delta w will come there. First thing, you initialize them randomly. You ensure none of them are 0. If they are 0, your W transpose X bar is of no use. And another one is, if you look at the activation function for varying, let's say your X here, you typically use it from -1 to +1. So typically you initialize these weights such that your function value will be in between -1 to +1, which would eventually would translate to, suppose I have an L dimensional features, okay, L dimensional feature vector, then this turns out that -1 by square root of L2 less than or equal to Wij less than or equal to, this is again a empirical one, which you could in fact not difficult to do. Assume an L dimensional space, assume that these two can have a similar values, and assume that this has to be -1 to +1. Okay, so if they are of similar value, you have such terms. If you have L dimensional terms, you will get L such terms. These two are in the similar range if you consider, and if you are looking for weight initialization, there is a square root coming. So that's why you would be getting something like -1 over root L2 plus 1 over square root of L. Am I clear? Input layer, there are L features. So if these two are same, I get L number of such terms. Okay, and then if they are of same range, you could consider this as L, W will be 1, or these two will be the same thing. So that's will give you square root of L. That's some empirically derived one. You initialize these weights by a uniform sampling or uniformly picking a random variable in the range of -1 by root L2 plus 1 over root L for the hidden layer. And the next one, suppose if you have k neurons in your hidden layer, what will you do then? -1 over root k less than or equal to Wij less than or equal to 1 over root k if you have more next for the next layer. That's all. You look at number of neurons there, square root of k, uniformly you sample and pick one of them. Okay, these are some important aspects that you keep in mind when you design your neural network. So with that, we stop our analysis and everything for neural networks. Then in the next class, we will look at another way of classifying things, which is referred to as support vector machines. This is what we will see from the next class. Okay, thank you.